This video is about the fundamental theorem of algebra and what is meant by multiplicities with the zeros. Let's get started. The fundamental theorem of algebra is that an n-degree polynomial equation has n solutions. Meaning, if it's a second degree or a quadratic, then it will have two solutions. If it's a third degree polynomial equation, then it has three solutions, or whatever the highest exponent is of the equation, it has that number of solutions, okay? But the caveat to that is that some of them may be complex numbers. Let's look at a few examples. Okay, in number one here, we have, let's see, if we found the biggest exponent, it would be x cubed times x to the 8th, which ends up being an 11th degree polynomial, okay? So I should have 11 zeros, okay? Well, it's kind of factored for me, so I'm going to use the zero product property to solve this. And I'll think to myself, what minus 4 equals 0? And the answer is 4. Okay, so 4 minus 4 equals 0. And what minus 2 equals 0? Well, it's 2. So I have x and 2. So I'm supposed to have, according to the fundamental theorem of algebra, I'm supposed to have 11 solutions, but I only find 2. Now, are they complex? Are they real? And truth be told, is it has to do with the idea of multiplicities. Okay, so there are, 4 and 2 are all of the zeros. There are no complex zeros, but it has to do with multiplicities. If you look at the exponents here, I have x cubed right here, which means that 3 of my zeros are all x equals 4. That happens more than one time. Okay, so we say that x equals 4 is a 0 with a multiplicity of 3. Okay, so 3 of my zeros are x equals 4. And similarly, I can look over here at this exponent of 8 and know that x equals 2 is also a 0. In fact, it's more than one. It's 8 of my zeros are x equals 2. So I would say that x equals 2 is a solution with a multiplicity of 8. Okay, so I do have 11 solutions. 3 of them are 4, and the other 8 are 2. Okay, let's jump down here to number 4, and we'll find a polynomial that has the following zeros and multiplicity. So the other way around, if they give us the zeros and multiplicities, can I find an equation that matches that? Well, I need a 0 of 2. I'll just name my function f of x. Okay, and to get a 0 of 2, I must have x minus 2 as one of my factors. Okay, and if it has a multiplicity of 3, then like I saw in number 1, I'm going to have this to the third power. So 3 of my zeros are 2. Okay. Now, to have a 0 of negative 4, then I need a factor of x plus 4. So if I plugged in negative 4, I'd get 0. And the multiplicity is 1, so I could put an exponent of 1, but usually we don't, so it's simple. Okay. Next is 0 of 6. I need a factor of x minus 6. Okay, and the multiplicity is 6, which means I need 6 of those zeros. So I do that with an exponent of 6. And then finally, I need a 0 of negative 8, and I get that from doing x plus 8. And if I want the multiplicity of 10, I need an exponent of 10. So it's not that challenging to go from zeros and multiplicities to a function, but that connection I think is pretty important. Now I can find the degree by finding the biggest exponent I would have if I multiplied this out. And I would do x cubed times x to the 6th times x to the 10th. Or in other words, I can just add together all the exponents. Okay, so I'm going to add together the exponents, and 3 plus 1 plus 6 plus 10 is 20. So this is a 20-degree polynomial, okay, that I have, okay? Now the next question in B, which I have kind of cut off here, is there more than one polynomial function that has the same zeros and multiplicities? Now, the answer actually is yes. Okay, and the trick is I need to multiply this times something that will not change my zeros or my multiplicities. And so I could add, not add, but multiply the whole function by some other constant 2, or 3, or 1/2, or some other variable here, not variable, but some other leading coefficient or some other multiple that would change, have a different function, but it would keep all the zeros and the multiplicities the exact same. Okay, I next want to look at number 5 to give an example of that. Okay, find two different polynomial functions that have zeros at 1, 3, and 5 of multiplicity 1. Okay, well, thinking through what I just did, I'll call this function f of x. Okay, and I'll have zeros at 1, and to get a 0 at 1, it's x minus 1. To get a 0 at 3, it's x minus 3. And to get a 0 at 5, it's x minus 5. Okay, and if they all have multiplicity of 1, then all of the exponents here would be 1, so I won't even write them, so it's in simplest form. Now, I need to find two different functions, and so I'll call this one g of x, and I'll basically have the exact same function with some other constant in front, like the number 2. So 2x minus 1 times x minus 3 times x minus 5. Okay, so the point of this video is that, first of all, you have the same number of solutions as the degree of the polynomial. And the second piece is that you can have 1 0 more than one time, and it's called multiplicities. And that has actually some really important implications in graphing that we're going to do next. All right, this video was about zeros with multiplicities and the fundamental theorem of algebra. Thank you for watching.